Well, if you're working in quality or manufacturing and perhaps your company is working with a new product, maybe with a new customer, or maybe you're even looking into a new market, maybe you've been given new responsibility, a new career challenge to build a quality system that provides for the best results possible. Your company has high expectations of you to get the job done right the first time. Well, if that introduction has some interest to you, I will welcome you to the Practical Problem Solving Clinic, Ongoing Controls. I'm Mike Vella, and I'm recently retired after 42 years in operations and quality. First 30 years working for an OEM supplier of safety critical parts. The last 12 years for a terrific food manufacturing company. Undergraduate degree in aviation engineering technology from Western Michigan University in Kalamazoo, and my MBA in finance from Wayne State University in Detroit. Proud to be a senior member and fellow of the American Society for Quality, where I was certified as a quality and reliability engineer. This session, called Ongoing Controls, is the sixth in our module on quality and productivity improvement. And here we have some detail on the 6 training modules. First is a structured problem-solving method called the 8D, or the 8-discipline problem-solving method. Next is an introduction to SPC, statistical process control. Building on the SPC training, we introduce something called understanding variation to solve problems. Then experimental techniques. These are very interesting discussions about how to improve processes using something called hypothesis testing and analysis of variance, ANOVA. In this module, we introduce the Taguchi fractional factorial technique, and then a focus on the process, and then finally what we're going to be talking about today, ongoing control. Our agenda is to speak about first, second, and third level control, talk about best practice gauges, and then introduce source control. In terms of building a quality system for a new product, you might consider 3 levels. First level would include policies, procedures, documents, systems development, work instructions, and audit systems. Notice that I put it on the base of the triangle because it's really foundational. Second level is when operating the process, examining the product output and feeding back to the process variables any changes in the process so you can make improvement ongoing. And third level, we're going to be talking about real process control and introducing something called source control. So I think about first level controls in 4 tiers as well: policies, procedures, job instructions, and documentation. So policies are written to define the approach and responsibility for quality. Procedures specify what is inspected and how often. Job instructions are a little bit finer in terms of they answer who does the inspection and how is it done. And then finally, documentation provides a record of the work. Once you're past writing your quality policies, and that's very important, it's a very important step, you have to step back and determine what's important in your product. Entering into that discussion is going to be obviously customer requirements, performance requirements that will manifest themselves into internal designs. Of course, you'll be looking at regulatory requirements, industry standards, and other things. What we're trying to determine here is how to determine what's important and to confirm that what's important is assured. You have to go through some kind of critical examination of the process and of the product. Let's start with the design. That design review is called a DFMEA, or Design Failure Modes Effects Analysis. Designs Failure Modes Effects Analysis. So it's a review by the engineers of their design. What they ask themselves in this Design Failure Modes Effects Analysis is how the design of their product could fail, assuming that manufacturing does the job right. The next step is what we call a Process Failure Modes Effects Analysis, a PFMEA. And so now we're looking at the process, assuming that the design is exactly correct, how the process and processing could go wrong. And again, we're looking for characteristics. In both of these cases, we detail the importance of the characteristics that we're measuring in something called risk priority numbers, or RPNs. Coming out of those two critical processes, and these obviously are done by teams working very hard and sincerely to understand where the weaknesses in the design and the processes might be, you develop something called a control plan. This is a result of the analysis of the RPMs. It's a determination of how and how often product characteristics should be examined and what gauging systems are required. Now, out of the control plan, then you write your receiving inspection, your laboratory, your in-process audit, all the inspection instructions. This is the real hard work that's going to be done to assure what you've designed has been produced properly and documented properly. These are detailed instructions that specify the who, how often, and with what gauging system the product is going to be assured. In addition to that, in these inspection and laboratory instructions, there's going to be a reaction plan if the product at that point doesn't pass. So examples of first level controls, as we speak about, you often are considering quality policy manuals, procedures, standard operating procedures, sometimes known as SOPs, manufacturing control specification, MCSs, recipes, technical standards, tooling design standards, machine operating instructions, and the rest. These are all first level, very important documents that come out of the examination of the DFMEA, the PFMEA, that cascade into the control plan and then fall into these instructions. These are great, but don't be surprised that I tell you that first level controls do not necessarily assure quality or control. Before we go any further, let's talk about measurement and gauging. Two general groups of gauges. On the left, variables gauges that provide variables data, very useful in the use of statistical process control. These gauges are going to be static gauges like the micrometer that's pictured to the right, or continuous gauges that you might consider like pressure gauges or atmospheric gauges or temperature gauges, something like that. You're going to be measuring pressures, dimensions, temperature, speed, some kind of variables data is going to come out of variables gauging of your product and processes. Simpler and usually cheaper and easier to train are attribute gauges. Here's an example of a snap gauge where it's called a go and no-go gauge. In this case, that shaft or something that looks like a shaft is going to go into the top gauge and it's too large to go into the bottom gauge. It's called a go no-go gauge. Just an example of an attribute gauge. In contrast to variables gauges, attribute gauges gives you discrete data. It's pass-fail. They're great for checking size or distance or angle. Again, it's pass-fail kind of thought process. What we're trying to do here with these gauges is to measure and assure that your processes are within acceptable limits, making products that are within specification. If not, you need to consider stopping and going with corrective action. So when we're using gauges, we have to consider measurement error. Measurement systems analysis, or MSA, assesses the adequacy of your measurement system for a given application. MSA answers questions such as, how well does a measurement system describe the difference from the observed measurement as compared to the actual measurement? Can the measurement systems adequately determine the difference between different parts? Is the measurement system stable over time, or does it drift? Is the measurement systems accurate throughout the range of parts? Can different operators achieve the same range of measurements on the same parts? When we're talking about quality and quality control, understanding gauging and measurement error is critical to the discussion. The old term, you can't improve what you can't measure. Let's talk about accuracy. So on the left, think about the target, and what you have there is accuracy. You're hitting the target right on the nose. To the right, clearly the grouping is tight, but it's off to the right. It's inaccurate. With a little shift of whatever you're pointing at, you could perhaps get that thing right on the target. On the other hand, when we're talking about accuracy, you also have to consider precision. It's another term I've just entered into the discussion. So on the bottom left quadrant, you have a description of something that's not precise. It's sort of on target, but it's certainly not in the middle. And finally, inaccurate and imprecise. It's off target and kind of all over the map. Try to describe accuracy and precision in this way. Clearly what you want to have is something that's accurate, that's on target, and precise, which means that it's repeatable. Let's talk about accuracy first. If you consider the graph, so you have a distribution of measured values, and the box points to the average of measured values and compares that, or shows a gap between that group of measured values and the true value. That gap is called accuracy, or the degree of accuracy or inaccuracy. So accuracy, the definition of accuracy or bias, is the measure of distance between the average value of the measurement and the true certified or assigned value. That degree of accuracy oftentimes can be corrected, but you have to know what that degree of accuracy or inaccuracy might be. Another description of measurement error is something called repeatability. Again, look at the graph. The box that points to average of measured value, and then you have this distribution of measured values. Now, the broader that distribution is, the worse the gauging system is in terms of something called repeatability. The previous slide we talked about accuracy, now we're talking about repeatability. And that definition is the consistency of a single appraiser to measure the same part multiple times with the same measurement system and come up with a repeatable measure. Accuracy, repeatability, now we're going to be talking about reproducibility. Again, consider the distributions, and they're all done by different appraisers, appraiser 1, 2, 3, 4, and 5. So reproducibility is the consistency of different appraisers in measuring the same part with the same measuring system. Accuracy, repeatability, and reproducibility. And finally, something called linearity. Consider a gauge you assume is going to be true throughout the range of its measurements. So consider that red line, we'll call that perfect linearity, no bias. As the true value and the measured value extend from the origin, the results are the same. An example or a graph of poor linearity, as the true value moves to the right, the measured value is not exactly on track. And of course, when you have something that starts off the zero part, we'll call that a constant bias. In this case, we've drawn it with the yellow line, a perfect linearity, but with its origin off center. We started our discussion about gauging and gauging error in terms of discussing accuracy and precision. So generally, precision is our most important concern because accuracy can be corrected through calibration. But if the gauges and the gauging systems are not precise enough, then we have bigger problems because that really contributes to unexplained variation. So once your gauging system has been calibrated for accuracy and perhaps the gauge repaired in terms of linearity, the sum of what we call measurement error is the statistical summing of the gauge error generated by, first, the variation within an appraiser, which we've called repeatability, and the variation between appraisers, which we've called reproducibility. I'm sure there are a number of sources to help you understand and deal with measurement error. One I would point you to is pictured in the lower right-hand corner, provided by the AIAG, the Auto Industry Action Group, and it's called Measurement Systems Analysis, MSA. This book will help you walk through an understanding of measurement systems analysis, but beyond that, there are a lot of computer programs that help you understand measurement system analysis and help you assess your gauging systems. Besides examining the variation associated with a gauge, how good of a gauge must you have? And I'd like to bring up the point of something called resolution. The resolution is the ability of a measurement system to discriminate between measurement values. So think about a rule of thumb, and that is the measurement system should have a minimum or produce a minimum of 10 measurements within the product tolerance. For example, if you have a product with a tolerance of plus or minus a half an inch, the minimum resolution should be 1/10 of an inch. You don't want to have something that you're measuring with a very, very coarse measurement system that is really varying in very, very small degree resolution. In-process gauging is very important. Think about race car drivers. They're not really looking at are they driving between 180 and 183 miles an hour, or maybe when they're shifting gears, what RPM they're shifting at, or when they're looking at their oil pressure, temperature, maybe boost pressures. They're looking at their gauges and trying to get a grasp of are they in the green or are they in the red. So design your gauging systems to be read as a glance, especially your in-process gauging. Remember that you're going to be measuring only a vital few items in your process. So focus on those items that are going to be controllable. Don't measure things that aren't controllable. And with in-process gauging, the way I've described, allows operators to have a quick determination of the direction and the amount of adjustment. And remember, in terms of total gauging error, more than 10% is not acceptable. Let's shift ourselves a little bit in terms of process and process capability and process control. A couple definitions. A process, we'll call, is a series of action steps, motions, or operations leading to some result in the manufacturing process. It's also considered a unique combination of machine tools, methods, materials, and people engaged in production process. Process control is the method of defining and monitoring key process inputs which accurately predict process performance. And ultimately, what we want to achieve as process capability is the ability of the process controls to operate the process, providing a continual adherence to requirements. This leads us to second level controls. Consider a process, very generic drawing there. Step 1, step 2, step 3, that might be a chemical process, a machining process, a mixing process, any process you might consider. Typically, it's more than one, step 2, step 3, and then we're going to stop and inspect. And at this point in the process, perhaps you're going to be employing statistical controls like statistical process control, SPC. And you're going to inspect and you determine whether the process is okay to continue or you need to stop. And you call this a feedback loop. Second level controls employ feedback loops, often using statistical controls. Let's talk about controls. So in this little matrix, we have in control and inspect in quadrant 1, inspect but out of control in quadrant 2, in control but out of spec in quadrant 3, and out of control and out of spec in quadrant 4. Clearly, where you want to be is in control and in spec. If you're in quadrant 2, out of control, and you're in spec, you may be in spec right now, but who knows what the next hour will bring. If you're in quadrant 3, in control and out of spec, well, that means you're repeatedly making scrap. And out of control and out of spec is a place you clearly don't want to be, because you're making scrap and you don't have any idea what the next move is going to be. Well, a little bit broader description, we're going to talk about in control, out of control, in spec, and out of spec, statistical analysis and capability analysis. So when you're in spec and in control, that means the process is repeatable and operating within specifications. Out of control and within spec is that you're not repeatable, but you're operating within spec. In control and out of spec in the lower left-hand quadrant means that you're repeatable, but you're operating beyond the specification limits. And of course, out of control and out of spec in terms of control and capabilities analysis is you're not repeatable and beyond specifications. So in terms of definitions, let's use these descriptions to help us guide our discussions in the future. So I mentioned earlier, second level controls imply that you're going to be looking at the product and adjusting the process. And so what is the process? Well, who knows, but typically you're going to have material, perhaps energy, environment, measurement, precision, people, and many other process inputs. And you're going to want to know what those variables do when you're operating the process, and we'll call those process inputs. Process inputs, you operate the process, you examine the product, adjust the process if there's a problem. And you determine whether it's okay to continue operating the process, or do you need to stop, or is it okay to ship? So at the end of that, there's going to be some reactions they have to take, and those fall into generally two major groups: manual controls and automated controls. Well, manual controls require your operators to have a very, very good appreciation for the process. Think about you driving your car. Clearly, if you're running off the road, you want to have, and you have manual control of your car, you must have understanding of how the car operates. So the degree of operator training is dependent on the process complexity. Are you driving down the highway at 60 miles an hour, or are you driving on a racetrack with other drivers that are doing 200 miles an hour? Process gets much more complicated as the speed goes up and the number of cars around you get closer and closer. Manual controls and degree of operator training is also dependent on gauge sensitivity and the expectations for the measurement following by corrective action and process verification. Then we move into automated controls. Typically, they have alarms. Your engineering and process control people will determine predetermined control limits on the process. But oftentimes, even automated controls, they must have quick human or machine intervention. And when you're using automated controls and operations are still running, be careful of something called over control, where let's say the process is running too high, it corrects it and it drops the power, and now it drops too low, and then as it falls below temperature, it pumps the gas and increases the energy, and now you get a big cycle of something called over control or the servo effect. So be careful with automated controls in terms of your reaction plan. Knowing full well that out of control process inputs will always result in out of control outputs. So let's talk about our process. We got three raw materials, raw material 1, 2, and 3, feeding into process inputs 1, 2, and 3. In our case, in a very simple case I'm describing here, raw material 1 is feeding into a process input that's out of control. There's no chance that if that process input is important to the process, that product will come out right. All the process inputs, all the raw materials have to be within specification, they have to be controlled, they have to be stable before the product comes out right. Consider your kitchen and you're baking a cake and you predetermine the temperature of the oven and you have the ingredients, the flour, the sugar, the mix, the pan, all the rest of the ingredients. Well, if that oven that you're going to be putting that cake into in a little while after you spend all the time mixing and blending, if that oven controller is cycling up and down, you're going to not have a process in control. Or let's just say that if you're making the product with sugar and you're taking maybe a couple of scoops of sugar out of one bag and maybe that bag is empty, and the next bag is a different supplier of sugar and that sugar is old or deteriorated or doesn't taste right, or maybe it's the wrong kind of sugar and you mix it in your batch, provides a raw material source that's out of control. These are really simplistic examples that I'm giving you, but I think you get the idea that your raw materials and processes have to be in control, or the likelihood of having good quality product come out of your process is slim. And you need to know how your process operates. I have a picture of a pilot and he's flying over wherever, and he's got hundreds of controls in front of him. I have no idea what those gauges are, but certainly that pilot must know how to operate that plane that he's traveling in and understand the reaction each one of those gauges or switches will give him if he operates them. So if you don't know which are the key process inputs, and if you don't know how they operate, and if you don't know their current status, it's going to be very difficult for you to predict continuous process control, which leads us to something we call third level controls. So third level control is, again, like second level controls, but moving the process controls upstream. Understanding, just like that pilot in the previous slide, understanding very intimately what each one of those controls and switches, gauges, telling the operator of the process to do, how the process is operating, and understanding that if they move this valve so much in this direction or change the raw materials to this degree or the energy of the environment or whatever of those key process inputs gives you a much better chance of having a positive product output. So the idea with third level controls is not so much to rely on the product examination and statistical process control to help you react to the process, but drawing further upstream in the process and control each one of the key process variables. That's where true process control is. I'm going to give you some examples that are not necessarily manufacturing examples in the next few slides. Let's talk about your plant manager. Plant manager's job is to operate the plant safely and produce a product meeting the customer's needs, and as a result of all that good work and all the team's work, provide the company profit, cash, and hopefully growth. Plant manager is focusing on certain very, very important operational items. They're responsible for inventory level, on-time delivery, product quality, absenteeism, safety, and on and on and on. All those things are measurables that the plant manager and the plant management staff is held against. And clearly there are many things that control all those items. The idea is not to simply measure and report in your plant manager's meeting, for example, the output, but to understand the controls of all those items. Control for inventory, control for on-time delivery. Focus on those controls that give you what you want in terms of inventory, on-time delivery, and so forth. And that is called sustainable process control, and we talk in terms of plant management. Another example, inventory. So why is inventory important? Well, the plant manager doesn't have the raw material they need. Operations doesn't have the right material that they need to do the job that they need to do on time in the right place, and they have a problem. So there must be certain inventory controls in order not to have too much stacked up in the inventory, drawing down cash, and it must be the right inventory at the right time. So what are those process controls that the people who are operating the inventory system must have? They must have a clear understanding of planned consumption. They must have accurate counts. They must have timely orders, on-time receipt, proper quantity receipts, security, proper storage, and so forth. So if the inventory managers are focusing on those things, upstream process control, that's a sustainable model that works to give you something called good inventory control. That then results in a sustainable profit, cash, and growth. But another example, safety. So we don't just measure safety by going to safety meetings. There has to be some process control that leads to something we call safety in a factory. Yeah. Right? So, what is the safety culture? Is it positive? Do people respect the idea of having a safety culture? It's management and leaders in the business leading by example. When there is a problem, it's exhaustive and timely safety corrective actions. It's safety suggestions, ideas for improvement coming from the people who are operating the system. It's safety audits, double checking what should be done, and corrective actions associated with the safety audits. Perhaps it's external experts coming in, called external validation, routine meetings and communication. These and many, many others are controls that provide you good safety. Safety just doesn't come out of the woodwork. It requires a tremendous amount of work And understanding those controls and operating those controls properly is a sustainable process for giving you safety that results in profit, cash, and growth. Point is, third level controls, not only in manufacturing, but in all elements of manufacturing quality, you need to focus on the process upstream. So the idea is to drive to the source so that you can have process capability, understanding those process controls that provide you good machine controls that then give you product in the shipping room and happiness for your customers. Understanding those process controls and delivering process capabilities, things that are repeatable over time. This leads to profound knowledge. By doing the hard work of understanding those process controls, I call that profound knowledge. Knowing exactly, like the pilot of that airplane, exactly what happens when they flip that second switch from the left on the lower panel, what that means and how far that will change the plane's attitude or direction or speed. Having a profound knowledge of the process. That's where we want to get to. Driving to the source, third level controls. We now move into something called source control, and I'd like to introduce the gentleman to the right, an engineer. His name is Shigeo Shingo. And he really opened my eyes. It was in the early 90s, and I was struggling with a process that was delivering to my customer something on the order of 30 parts per million. Now, you might think 30 parts per million defects is not such a bad deal, but in the automotive arena I was working in qualities, 30 parts per million was not acceptable at all. I was working very hard with statistical process control and documents and procedures and driving to the source, but I was not getting that breakthrough that would take me beyond 30 ppm. So I read his book that I'll be introducing to you in a minute, ZDQC, Zero Defects Quality Control, and the idea of human error and how they lead to defects. And Shigeo Shingo said that it is impossible to eliminate all errors from any task performed by humans. I kind of knew that, but to have someone else say it and read it really knocked my socks off. He said that errors can, and often do, become defects, and we need to separate the concepts of errors and defects. We introduced three types of inspection. First is judgment inspection, and that's when you separate defective products from the good ones after processing. Pretty wasteful. But it does prevent defects from being delivered to customers, but certainly does not decrease a company's defect rate. So now we're just talking about sorting, and if you think sorting is 100% effective, you might be fooling yourself, but that's the concept of judgment inspection. Informative inspection is a process where you investigate the causes of the defects and you feed back this information to the appropriate processes so the action can be taken to reduce the defect rate. Sounds reasonable. But again, the process is producing defects, and unless the inspection is perfect, you're going to be shipping defects. And finally, source inspection, or maybe another way to say it, inspection at the source. And Shigeo Shingo says that source inspection is a defect is a result or an effect usually caused by a simple mistake. Through 100% inspection at the source, the mistake can be corrected before it becomes a defect. Therefore, defect zero can be achieved. Talk about this a bit more in a moment. So in a book I'm going to be introducing to you in a moment, they made a survey, talked about the causal connections between defects and human errors. Across the top, human errors that they surveyed: intentional, misunderstanding, forgetful, misidentification, amateurs, willful, inadvertent, slowness, non-supervision, and surprise. And perhaps you could put in a few more, but in this survey, they surveyed those. And the types of defects, and maybe these apply to your assembly operations: omitting processing errors in setting up the workpiece, missing parts, wrong parts, processing wrong workpieces, misoperation, adjustment error, improper equipment setup, improper tools and jigs. And in their survey, in their analysis, between these two factors, they made relationships, and they colored them green in this case as strongly connected, and yellow connected, and if there's not much of a relationship, it's blank. And so it's surprising, certainly was surprising to me when I read the book for the first time, is that the high degree of inadvertent errors related to causes of defects, inadvertent errors. So we talked about a typical manufacturing cycle. Again, an error takes place, a defect is a result. There's a feedback loop, corrective action, perhaps we're sorting. Certainly we're still manufacturing parts that are defective. Who knows what's in the shipping room? And he contrasts that with what he calls source control, or control at the source, where an error takes place. It's a cause. We have feedback on the error, not on a defect, and there's corrective action. The idea is that errors don't result in defects, and if you don't have defects, then you don't ship defects. Two texts I would direct you to, and the sources and the detail are at the end of this presentation. First is Pokeyoke, Improving Product Quality by Preventing Defects, and Shigeo Shingo. Between these two books, besides the interesting reading, there are 400 illustrations of mistake proofing, and I'm going to go through a few of them in a few minutes. But the concept of zero defects quality control is, again, source inspection, which checks for factors that cause the errors, not the defects. 100% inspection using inexpensive mistake proofing devices to inspect and automatically for errors in defective operating conditions so that you don't get the defects in the first place. And of course, immediate action where operations are stopped instantly when a mistake is detected and not resumed until it's corrected. Two books, and the references are at the end of the presentation. How about a couple examples? Now these are just photographs of one of many of the examples. For example, in this case, they have on the left-hand side a plate, okay? And there's potential for this plate to be reversed, left to right, up and down. Again, inadvertent error. The proper way to assemble the plate or have the plate ready for further assembly is in this direction. Well, there's a slot, therefore, in the bottom, and if you simply put a positioning pin, as illustrated on the right-hand side and pointed by the green arrow, that's the only way that that plate can go in the fixture. So therefore, it's impossible to start that process with the plate in the wrong position. So this is called a prevention control, as it prevents defects from occurring. Source control, preventing defects. Using this operation, this control for this operation, the operator might, in an exact way, try to put that plate in the fixture one way or another, but it can only go in one way, the correct way, preventing defects from occurring. Here's another example. In this case, these are detection modes. So on the left-hand side, this is sort of the before and after, left and right. There's this, whatever this is, this boss on the right-hand side, and it could be staked in or welded in, either on the top or on the bottom. But by having a fixture where there is, in this case, a limit switch, where that pin or whatever that item is only can operate, in this case, maybe the next operation, a staking operation or a welding operation. With that limit switch pressed, that means that little item there on the right is in the right place. Again, this is called detection. So it detects whether this item is in the right place. Inexpensive sensing devices in your fixtures help you detect if the process is operating correctly. And finally, immediate action. So in this case, there is a multiple drilling operation on this plate, and there's more than one drill drilling holes at the same time. And if one drill breaks, you want to know about it. So perhaps below the drill bits in this fixture is a sensor, and if the drill bit is broken and doesn't go all the way down, striking the sensor or coming close to the sensor, it shuts down the process and none of the drill bits can operate. It's called immediate action. So we talked about three elements: prevention, detection, and immediate action in terms of strategies in zero defects quality control. Again, in these two books, and I'm sure there are other books on the market, but in these two books, there are 400 of these illustrated examples to give you some idea of how maybe to drive your process towards zero defects quality control. So weighed by importance is source inspection, and obviously they called it source inspection and the preventing errors from becoming defects. Shingo said that this is 60% of the package. 30% in his experience was inspection, detecting errors before they become defects, and of course, immediate action is the rest. With a great emphasis on source inspection and 100% inspection, preventing defects from becoming errors. I got to tell you that once I was able to implement Shingo's concept on this process, we were able to drop that 30 parts per million down to 0 ppm and maintain that level for years. We would have issues once in a while when the mistake-proof devices failed and required maintenance, and that required a whole other correction action plan. But this process of zero defects quality control and using these examples illustrated in these two books was a huge leap forward in developing zero defects in our quality systems. So in summary, hope to have introduced in this package called Ongoing Controls. I introduced to you first, second, and third level controls. We talked a bit about gauges and then introduced Shingo in terms of source control. If you have any questions, please write me at the email address. I want to thank you for your time and attention. And here are the references I spoke about in the presentation: Zero Quality Control Source Inspection, the Poka-Yoke System, produced by the Productivity Press. Improving Product Quality by Preventing Defects, again by the Productivity Press. Measurement Systems Analysis by the AIAG, the Automotive Industry Action Group. And again, Failure Modes Effects Analysis by the AIAG, the Automotive Industry Action Group. Thank you very much.